I hope you can see my screen. I'm going to talk today about large language models and natural language processing and its intersection with material science, sort of broadly. I'm going to focus on literature, though. So by the end of today's talk, I hope to sort of talk about the following four things. And there's so many, it's actually hard to pick, right? To down select what's going on in this world right now. But I'm going to start by giving an overview of how we have traditionally extracted materials data from the literature, right? Then I'm going to talk about what is the current state of the art using language models. And then I'm going to pivot to saying, okay, it's not just about extracting data, but rather how do we pull knowledge out of literature, right? And we can do that with language models. And finally, I'm going to talk about how language models are enhancing and modifying at least the way that we are doing research in my own lab. And I'll give it a specific example tied to generative models for that one. So let's dive into it. So first off, materials data is really important. We can see examples of the value of having this type of data and when we don't have it. For example, here's an example. This is the IUCR when they first defined the sieve file, right? I think this came out in 1991, if that paper's right. The sieve file is the crystallographic information file. It was a standardized way of dealing with data. And by having that, it allowed people to build up databases. The ICSD, the ICDD, the Cambridge, all these other ones sort of emerged because there was one agreed upon format for crystal structures. And we don't have that for materials. I wish we did. There is not an agreed upon format for presenting materials properties, materials microstructure, any of those different things, which is a bummer. So what do we do? What we do is we have to sort of scrape that data from the literature by hand, and that's hard to do. And it's actually a pretty young field. I was surprised just how young. The field of sort of semantic text mining in the domain of chemistry and materials, it only goes back like 15 years. These first sort of initial papers showed up in like 2011, 2012, which is wild. So these were things like Oscar or Chem Data Extractor, Chemical Tagger, and these were just okay. They really relied on named entity recognition. So if you put in a certain formula, it would look for that formula in the text and grab it, right? For certain things, it worked okay. If everybody were to describe materials in the exact same way, it'd be fine. But that's kind of hoping for something that isn't reality. In reality, people describe it in all sorts of nuanced language. And so these first sort of tools that showed up weren't very good, but they got a little better, right? To try and tackle this complexity in description, scientists started turning to natural language processing, right? Not just named entity recognition, but now they're using some of the first early language models. These were not anything like the large language models we use today, but they were a little better. And the paper on the far right, that was presented in 2017. And I remember going to that talk. It was at the fall MRS meeting. I went to it and I remember seeing this talk where they were trying to pull data out of the literature. And I remember thinking like, boy, that's a hard problem they're trying to solve. And this is a good approach, but I don't think it's going to work. Right. I remember thinking I personally in my mind resigned this to be one of the grand challenges of informatics. Like maybe one day we might eventually be able to pull data out of papers in an effective way. And I don't think that's ever going to happen, but maybe one day I thought. Well, that was in 2017. What happened in 2017? The other thing that happened in 2017 was the creation of the transformer architecture, which I'm sure, I've missed most of these talks because I was sleeping while they were going, but I'm guessing the vast majority of what's been talked about has relied on transformers. It was a game changer. All of a sudden, with the birth of transformer architecture, you saw the creation of things like SciBERT or ChemBERT or MatSciBERT. These are now language models. They still weren't very big, by the way. The number of parameters was far, far smaller than what we're using today. But these are way better. Now we can learn about words in the context of everything else, not just in some sliding window or the other limitations we had before. And this was a real jump forward. And all of a sudden, it started to look like this was a possibility. The paper that changed my mind, that made me think that this is a grand challenge that I don't think is ever going to be solved, to one that I realized, holy smokes, we can actually solve this problem. It was actually a preprint in December of 2022, so not much later after that. It was later published in Nature Communications in 24, but here's what they did. They were only looking at abstracts and they were pulling structured information out of the abstract. So that's limited, right? It's not the whole paper. There's limitations. And there's limitations what they did. They had to hand label 100 examples to build a partially tuned model, right? And then using that partially tuned LLM, they were able to create another data set of about 500 examples where they would sort of babysit it and fix the things that it got wrong. And once they had all those examples, then they could actually do a proper fine tuning of this language model. They were using GPT-3, not ChatGPT or anything. This is GPT-3 to get their fine-tuned model. And it worked. It's pretty darn good. It's limited on token size. It's limited on a lot of things, but it was pretty good. So it changed my mind on this. And then lo and behold, you start to see a bunch of papers coming out doing the same thing, right? Extending it to lots of niche fields. Here they're doing it for perovskite solar cells, lit review, pulling data out of that. But another big breakthrough came with ChatGPT, right? ChatGPT is different than GPT-3. Actually, GPT came out in like 20, whatever it is, 18 or something. And some people didn't even notice it. But in 2021, when ChatGPT rolled out, that was a big change. Here, what they're doing is they're relying on RLHF, which stands for reinforcement learning from human feedback. So it's different. This is not just the language model. This is pairing the output of a language model with a human-based scoring system. That's the reinforcement learning model, right? There's a reward system. So in other words, you take a model that's able to take an input and generate some sort of output, right? So it's capable of doing that. But then you say, all right, for a given prompt, let's have it generate a couple different responses, for example. And then a human would actually look at those responses and rank them. Here's the best, all the way down to the worst response for that given prompt, right? This is where you can program alignment, for example. If you don't want it to use swear words, if you don't want it to talk about sensitive issues, this is where you can penalize it for doing that. And the reward policy, right? They're using PPO reinforcement learning algorithm to do this, really improved our ability to pull information out of literature in the way that we want to, right? So with this sort of chat GPT style thing, all of a sudden you saw lots of text extraction happening in literature. Here was one applied to MOF synthesis. Here was another one applied to sort of a general purpose LMs for, it's a model agnostic method for materials data extraction. They tried a couple different ones here. And the point is that it was starting to look pretty good. So that brings us to the sort of state of the art. We went from thinking that this was not a solvable problem to realizing it is solvable, and it's actually pretty not that difficult. So what's the current state of the art, and what can we do to push this even further? Well, when it was December 2022, when I saw that paper, the preprint on using GPT-3 fine-tuned to pull data out, we decided to give it a shot, right? That very next month, I held a hackathon, and we decided to spend our time at the hackathon doing just that. And you can see what it can do, right? The paragraph on the left came from a synthesis section, the methods section, because remember, they only pulled from the abstract. We said, well, how's it going to do on something a little more rich in material metadata information, like the synthesis methods section? And yeah, it seems like it does a sort of okay job. So we started to think maybe we ought to, double down on this and try and improve it. So when we're thinking of improving it, we had to identify the problems with what they had done previously. One problem is they were only looking at the abstract. We want to look at the whole paper. That means we have to deal with the token size limitation, right? So we need some way of dealing with the token size limitation. We'll deal with that. And then the other thing that we need to deal with is, okay, they hand labeled 500 examples. Well, they did hand labeling on 100, then they babysat the other 400. That's still a pain in the butt. Like, I don't want to do that for 500 papers. So what if we could find another source of labeled data? Here's our idea. We said, what if we pull the DOI from a PDF, some article? From that DOI, we should be able to get the PDF, or ideally the XML if it's available. So now we've got the article text. Then we need to pass this through some sort of data reduction, right? So that we can reduce the token size. Meanwhile, if you have the DOI, we might have a polling file entry for that same article. Now, the polling file is they've paid human experts to read that article to pull out materials data. So we thought that that could serve as our labeled data. So I don't have to do it by hand. I can just link it to the polling file entry. That should be able to be the training data for our GPT-based model. We fine tune it, and then we can take all sorts of new entries or existing entries, pass them through our model, pull out the data, and make a repo. That's the concept that we had. So there's some tools along the way that make this easy. For one, Meta released NuGet, which is Neural Optical Understanding of Academic Documents. It's basically a PDF reader. It's awesome. It can take PDF and convert it via optical character recognition to LaTeX. It can pull information from tables really effectively. Like, here's an example. On the top, you see a table, a typical table in a material science paper. It was able to convert that to LaTeX tables, which are black magic anyways, like those are complicated to make. But if you take that and then you run it through LaTeX and you have it recreate the table, you see that it has excellent reconstruction. So it's doing a really good job, which is awesome because a lot of times information is stored in these tables and you have to sort of like line things up. And we can do that by hand, like by eye. It's harder to train an algorithm to do that. So it's awesome that these sort of tools are showing up so that we can extract data from these things. And then we said, all right, I think we've got the tools to sort of dive into this, but before we attempt it, maybe we better understand where the data lives in materials publications. So we published this nice perspective piece in Matter where what we basically did is we looked at, I think, 10 different articles, and we said, in these articles, where does one find materials data? Is it in the figures? Is it in the tables? Is it in the text, right? And you can see that if we look at text, it is typically very high variety, lots of different types of data from processing parameters, performance parameters, characterization numbers, named entity recognition, named entities, excuse me. But it's also very complex, right? High variety, high complexity in the text. The tables is much more structured. It tends to be less complete. The types of things we find there are not quite as complete as what we find elsewhere. Figures is definitely the place where it is the most rich in data points, but it is lacking categories. For example, named entities may or may not be there. Characterization is often there, but it's poorly described. The structure is not ideally what we're looking for, but there's a lot of data hidden in these figures. And by a lot, you can actually quantify. Again, this was looking only at 10 papers, not like the entire field or anything. This is admittedly a subset of what could be out there. But what we find is that named entities predominantly are found in the text. So is processing conditions. Then you also find some characterization performance. In the tables, you don't find processing conditions typically, very low, but you do find lots of characterization details. And then performance is predominantly in the figures. And that's unfortunately probably the data that we want mostly is the performance properties, at least for many machine learning. If you're going to try and pull data out of the article to do machine learning with it, that's often what we're wanting. So that's a bummer because we don't have great tools for pulling information from figures yet. It's coming. I'm sure it's coming, but it's not really here yet. Okay, so the takeaway one, yes, it's possible to go from PDF to text for mining, but you're probably not going to find all the data that you want in the text. That's a takeaway for you. Okay, so now you say, what about the token size reduction? So you could do rules-based. You could say like, okay, take the entire PDF that you've turned into text, and you could look for anywhere where there's a number, keep it, plus the words within some window of that. That would be one way to do it. Now that's not great because you're going to lose a lot of context and like maybe they were saying it's not like that and you just got the number, right? So that wouldn't be ideal. So there's better ways like extractive summarization using hand labeled data or zero-shot summarization with no prompt engineering or one-shot summarization where you're going to provide a prompt. I'll show you some examples of these. For example, here is zero-shot summarization. I provided a prompt. I say, summarize the following text, and then I give it the text, right? And you'll see that it's able to go from our input, which was 157 tokens, and it squeezes it down to 58 tokens. So pretty good, threefold reduction. But if you look at it, it's also left out some probably important information, right, in its summarization. So now we're going to do zero shot, but we're going to give it better instructions. We're going to say, okay, I want you to summarize it, but make sure to concentrate on and provide any pertinent performance metrics, measurement results, or related numerical data while also keeping the information concise. Check it out. It goes from 157 down to 50. It's actually smaller, but it's keeping all the values, like the Bohr magneton values of this material are being included. All the phases, different named entities are being included, so it's doing a better job. But zero shot also, it's a stochastic process. And so I just showed you a good example, but there's plenty of times where it does a bad job, where it will either extract nonsense, it will hallucinate, it'll just fill it with empty cells. That certainly happens sometimes. But that said, I would say that it certainly has the capability of not only extracting things, but doing so in an intelligent way. It will categorize them in an appropriate way. Here it's putting chemical compounds together, processing conditions are getting put in the right spot in their own dictionary, characterization as well. So it looks very promising when it doesn't hallucinate or just fill it with blank spots or filler data. Okay, so takeaway number 2, I would say we're definitely going to need to fine-tune models for material science data extraction. Generalized LLMs are just not very good for this. And to fine tune it, we're going to need some gold standard annotated data sets. That is a time consuming and expensive task to do. Bummer. Okay, that's takeaway number 2. So let's think about providing some labeled data where we don't have to do it ourselves. We were hoping that the polling file would be a great answer to this, but it really contains highly cherry-picked data. Like if this was the table provided in the article, they might only take one or two of these values, right? Or if this is what was generated from an article and you looked at the actual figure, like maybe they took a measure of resistivity and it was at 330 Kelvin, but there might have been 10 other measurements there in the paper. So they're really giving you like a flavor of the properties. They're not giving you all the properties from it. It was a bit of a bummer to look at that and realize that it is a very pared down version of the materials data that's actually in the article. So we need something better. We had the idea to try out Google's Gemini Pro, which has a really nice workflow for doing structured prompts. If you're not familiar with structured prompts, basically you're asking it to do something. That's what the prompt, right? You're telling it you're a lean, mean materials data extracting machine, right? Here's what I want you to do. But then you also, the structured part of that says, for example, had this been an input, and you give it an example of text from literature, you say, here's what I would have expected as an output. And there you put an example of a JSON output. This is different than the fine tuning that I showed you from Dunn's paper, preprint in 2022, because they did it for 500 examples. And here we can get away with doing it for like 10 or 15, like way fewer, which makes this a lot easier. And the outputs are pretty good, right? So here's an example, like had this been an input, we would have said, here's an appropriate summarization. We sort of provide an example of the token size reduction. But you can do the same thing with structured organization. If this was the input, I want you to convert it to a JSON file, focusing on metadata for materials. Does a pretty good job. Again, we had to provide, okay, so we tested it on 10 papers. We ran structured prompts. For the paper, we only did 5 examples. And by the way, for each section, we also ran it 5 times to look at the variability to see how much uncertainty there was when this happened. And then we generated these 5 outputs with a hand-labeled reference that our research group put those together, and we scored the performance. And by score, there's different criteria that you could use for score. Like the simplest is the Rouge score. The Rouge score just is basically a measure of precision, right? And recall, but it doesn't take into account context. So for example, if the model spit out the hello, a cat, dog, fox jumps, right? Those words, and the reference text included the fox jumps, then it would look at the output and it would say like, okay, the word the, fox, and jumps are all there. So it had 3 words that were correct out of the 7 total. That's a 43% precision. And in terms of recall, you could say it had 100% recall. All of the words I was looking for are there. It just had some other nonsense words. So you could calculate like an F1 score. Rouge score is okay, but it's not great because what if they used words that were sort of similar? It should get like partial credit, right? For example, if the reference was the weather is cold today, and then the output was it is freezing today. Well, freezing and cold are kind of similar. It's not the same word, but there's a contextual understanding there that it's similar, right? So to capture this context, really you should be using something like BERT encodings. And so BERT score is a commonly used way of scoring these things because it captures not only context, but order. Like, are they in the correct order? It's capturing that. So this is a better metric to use. And essentially, when we look at our evaluation metrics, the Rouge scores are not amazing, but the BERT score is pretty good. So even with very few examples provided in your structured prompt, you can get away with actually a pretty good model. Okay, so takeaway number 3 here is that structured prompts could greatly reduce the manual annotation step, at least in my opinion. You don't really need to have the polling file or a bunch of human labeling. You can get away with a pretty small amount and have it work pretty well. We would love to have you follow along with this. This was published in IMMI, where I am the editor-in-chief, starting in 2 weeks, which I'm pretty excited about. So if you're considering of doing work in the area of large language models and chemistry and materials, we would love to see your publications there. I'd be happy to send them out to review. Okay, so what we've covered so far, I think I've got maybe 15, 20 minutes left. Feel free to stop me. But I'll say that we have large language models that we've shown that are pretty good extracting data from literature. Now let's ask the question, what about extracting knowledge, right? What about interacting with literature in a different way? Clearly here, we're going to talk about RAG, Retrieval Augmented Generation. I'm guessing this has already been covered in the course of this 2-day event, but very briefly, I'll just say that instead of just asking a question to our pre-trained large language models and hoping that it can find the right answer in somewhere in its previous training, you instead say, all right, let's pose the question, and our language model becomes, eventually it's going to give us the answer, but first we're going to use this idea of a smart retriever, which is going to look at some specific knowledge base and find what are the most relevant documents that would help answer this question that the user asked. And then you send the question and these relevant documents, some small subset, considering token size, over to the large language model. And you then basically say, okay, large language model, the user has this question. I think the answer is found in one of these paragraphs. Go ahead and provide a response. And it does way better than if you were to just ask it without providing this specific knowledge base. Really, this is, I think, one of the biggest applications of language models is RAG systems are really fantastic for giving you expert advice within a specific domain. Okay. Now, they're not that hard to put together, but there is a learning curve to it, and we wanted to make this even easier. And so my student Hassan just published this RAG skeleton, which is essentially a framework for building out these sort of RAG processes. There's some key things I can mention about it. First off, it's modular, makes it really easy to customize and integrate with other models. Has excellent domain flexibility. Obviously, we are material scientists, but you could use this for anything. Lots of compatibility. This will work with both local and cloud-hosted language models. For example, we have a grant from the Steel Founder Society of America where they have an awesome database of documents, but they really don't want to be sending that data even via secure API to somewhere like OpenAPI or OpenAI or anything else. So instead, we are building a local one with our own models, and this works great for either of those scenarios. And then lastly, it's scalable. It's meant to be, you can scale this for lots of different things and it will work great. So here's an example of it. Let's try it out on some real materials data. Here's a couple of nice review articles on perovskite solar cells. We can go ahead and load up an example of this and let's take a look at it. So here he's running it through command line, but you could build a simple GUI with SQLite or whatever else you'd like very easily. So the model he's using is an open model. It's Llama. It's a 3 billion parameter small model. It's a pretty good one though. He sends a temporary API to it. It found the knowledge base and it's like, okay, go ahead and ask your question. So he's going to ask about perovskite solar cells. He wants to know what's, the leading efficiency improvements, what's causing that. And it answers that very accurately. This sort of response looks really good. It finds actual articles, gives real numbers, doing a great job. Here he asked another question. He's like, well, what about encapsulation methods to influence stability and efficiency? What do we know about those? And again, it's able to provide like really good responses. This is a great example of what RAG is doing to help people who, you can read that article, but I just raised this to point out that there are like tens of thousands of articles in every single subdomain of material science being published every single year, and we can't read them all. So I love the idea of tools like this that are able to do more than just a Google Scholar search where it provides like, here's articles that have the same keywords that you're searching for, and instead can help us query and access information and knowledge held within those articles in a scalable way. I think this is really, really exciting example of Gen AI for materials. Okay. All right. By the way, if you didn't like to do it via the chat bot, it's via the command line. It's also very easy to build these out in chatbots. Here's one we did for a mineralai.net website that we put together, which allows people to query elemental resource information like cost or who's producing something, how many reserves are there market share information provided or things like that for the whole periodic table. It's trained off of the United States Geological Survey. And the point of me showing this is to show there's this cute little, chatbot dialogue bot that allows you to query this information in a sort of, it's like you're talking to like a customer service agent. It's very nice and easy to use. And this was both Hassan and Trupti, my students who put this one together. The source code for RAG skeleton is available now. You can check it out. It's easy to install. It's easy to modify. We think that this is going to be something that we hope a lot of people will use. Okay, in the time that I've got left, I want to talk about how we are using language models to enhance and even modify our own materials research here at the University of Utah. So we have recently published a paper on generative models for predicting new crystal structures. There's been a couple of these papers in the field, right? DeepMind's genome paper was the big one. There's been MatterGen, there's MatterSim, there's a bunch of these out here. We think ours is very good. We are using a crystal-tense representation, which you can read about in this paper. The point is that it was good, but it was also unconditioned. Basically, we trained on a bunch of data, and then the model will just return things that look like what it was trained on. It won't return only specific things. Like, for example, it won't return only the perovskites. It'll just generate things. And if there are perovskites in your training data set, it will return some perovskites, but not only perovskites. How great would it be if we could instead say, okay, here's the prompt that I want to give you in text, human language. I could say, generate a perovskite material with a certain band gap, maybe like 1 EV or something like that. That's different. Now you're taking something which is how humans think about this problem. We think about it in terms of language, right? We use human language. Well, we could take that human language and we could make that the conditional statement for our generative models, right? Now, there's a little bit of prior work that suggests that this is possible. For one, there's this Crystal LLM by our friends Louise, Keith, and Ricardo over in the UK. Really cool idea. It's not a large language model, so I don't know why they called it Crystal LLM, because really they just use autoregression. In other words, they just use like a transformer decoder network to do this, but still, what they do is they train on a bunch of civ cards, which are language, right? And given a lot of examples of those, then all they have to do is provide the first entry of this civ card, data K1BR1. Basically, they're telling it the formula, and the LLM, it's not an LLM, the autoregressive model does the rest. It spits out a civ card, and it wasn't actually terrible. The output of this is not that bad, right? A little closer to what we're imagining is this paper that just barely came out, right? This came from the good folks at Meta and NYU. And here they actually used a large language model instead of just a transformer decoder. They're using Llama 2 with 70 billion parameters. That's a big model. And they did a couple things which are kind of curious. Instead of taking the entire CIF and giving it the entire CIF to the language model, they just pulled out the relative information. I don't know if this was for token size or for, I don't know why they did it, but they did. So like, for example, like these values here in this green box, you can see that got the lattice parameters 5.1, 5.1, 5.1, whatever else, but they haven't labeled what's what here. And so the language model is given information without the context of what that information is, which was a curious choice. It's also a really big model, but they only gave it 120,000 examples to learn from. 70 billion parameters and 120,000 is going to be pretty tight. And so what they're able to find is like, does it actually do a good job of, following the formula, the space group, the energy hole? It doesn't. With 5 or more atoms, it doesn't do an amazing job. Only 61% of the time is it satisfying its criteria. And as you grow the number of atoms, that really falls off. The space group's really doing a bad job. So it's an interesting idea, but I think that we could do better than this, right? And so here's one thing that we considered. Well, they were trying out this Llama 2 70 billion parameters that came out in July of 2023. It is a huge model, 70 billion parameters, but if you look at Llama 3.1 with only 8 billion parameters, significantly smaller, you get basically the same performance, which is the sort of y-axis, right? So we asked ourselves, like, maybe we could take that model and we could use it. Now, you're not going to use that model, which has been trained off of, the internet's worth of data, and try and use it on civ cards without some fine tuning. You do have to fine tune it, saying, okay, here's actual civ cards and here's the structures which should be generated from them. But that, if you're going to use that model, it's got 16-bit precision. That is a huge model. It's a lot of memory. So we're not going to do that. Fortunately, there's good other options, right? Low rank adapters are a pretty good way to get around this. There's 16-bit low rank adapters, and there's QLoRa 4-bit precision. Essentially, what this does is instead of learning the weights of this large language model via fine tuning, you freeze those weights, you lock them, and you learn these proxy weights, right? These adapters. And then you concatenate those together. These proxy weights are a lot smaller in dimension, right? Instead of, for example, the Foley one for the model we were looking at was a 4096 by 4096 matrix of our query, Q, and value parameters. That's huge. So instead, we learned 2 different 496 by 16, or even smaller ones by 4 networks. And what you basically see is huge improvement in your training because the memory is a lot smaller. But you do see a trade-off. There's always this trade-off, right, in terms of performance. And you don't see a big drop-off with LoRa. You see a more significant drop-off with QLoRa, but it is much smaller. Okay, so this is what we're calling it CRISP-TeXT, right? Here's the architecture for it. We are taking our pre-trained model, again, 8 billion parameter Llama 3.1. We do a 4-bit quantized version of that, and then we apply QLoRa to do these low rank adapters so that it trains in a reasonable amount of memory. For example, we get away with, like, I think it's only 16 gigabytes of memory that this is using, which is very reasonable, using a batch size of 32 entries at a time. Then we're able to take a database of stable materials. We're using the MP20 or whatever it is from Materials Project. We pass it through CRISP-TeXT with a very specific set of prompts. We say, all right, I want you to generate a sieve for the given materials description. And then the input from the user is the description. It might be like, hey, the material composition is whatever. It has a space group number of something like that. We're going to start with that simple example first. And then it's able to output a sieve card that matches that. And it does a pretty good job. So you do need data to do this. Here's the data we use, the MP20, that's the Materials Project data set, which has only up to 20 atoms per unit cell. That gave us about 27,000 sieves for this. We gave it a very specific prompt. And then we had a constrained type of input that users could give. Basically, they could give the formula and the space group for now. And then you have another data set where we said, okay, don't give it formula and space group. Instead, let's have it conditioned off of some sort of property. Now, normally they would treat that as a regression, and they would do the conditioning with that. Here we're using text as the conditioner, but we're describing a property like only give me things with energy above the whole equal to 0, meaning they're stable. And what we find is that this works pretty well. Let's watch a brief little video on this. So again, it's going to overview what the architecture looks like, what model did we use, how did we fine tune it with reduced, adapters, what data did we use, what were the prompts, and what's the typical output. Now let's actually see it in action. So what you're going to see here is, here's Chris text. So what the input was, okay, I want a material composition that has here neodymium, silver, mercury, whatever, and it has a space group of 225. First thing you'll notice that the space group here is just P1. That's because Materials Project uses P1 for everything. And then later on, once you have the simplest structure in primitive right here, in the lowest symmetry, then you can identify the space group afterwards. But it's populating ABC, alpha, beta, gamma, the atomic sites. It's doing a great job. And then afterwards, we run it through PyMatGen to figure out that, yeah, sure enough, the structure that was generated would in fact be 225. And it looked like a real material. Like this looks like something that you'd expect to see. So pretty cool to see it in action, how this would actually work. Now, how good is it? So we tested this on the same data set that the diff CSP paper used. So just so it was an apples to apples comparison, we used the same data set where they had 9,000 sieves, and we generated them, and then we asked whether it matched them, right? When you generate a structure, does it match the real one? And by match, you can actually define that. We use the structure matcher in PyMatGen with these parameters, like the site tolerance has to be within 0.5, the fractional length has to be within 0.3, angle has to be within 10. And what we found is that if you only generate one time, the match rate is 57%. But if you generate 20 times, then of those 20 samples that it generated, one of them is a match 73% of the time, which is pretty good. And you can actually also quantify the RMSE basically based off of atomic distances, and it's pretty good. So this is actually really surprising that even on the first shot, it gets pretty good. And within the first 5, you're basically diminishing returns. You're already very good. So your odds of generating are quite good. And you can see that. Here's some examples of ground truth actual structures, for example, right here, compared against the generated structures. And it's amazing. Now, some space groups are better than others. Like this first column is the space group 225. For whatever reason, in the database Materials Project, there's tons of space group 225. So the error is tiny. Like it had a lot of examples of that. In other ones where you didn't have as many examples, the errors are a little bit larger. But overall, this is really good. It's doing a great job of matching them. Sometimes it would generate a structure which, the structure is technically valid, but it didn't match what we were looking for. Like, for example, the sodium cobaltate. The sodium and the cobalt got switch their atom positions. So yes, it's a valid structure. It has the right formula. It even has the right space group, but the atoms are in the wrong spots. And you see a couple examples of that where it would not satisfy the matching criteria. Other times where it delivered an invalid structure, it can do that for a variety of reasons. For example, on the left, you see the actual sieve card for some compound, and on the right, you see the generated one. And when we open up Investa, it looks like some of the atoms are missing. Well, we look into the sieve card and check it out. Instead of putting positions for X, Y, Z, it put some letters, right? So that returned an invalid string, right? An invalid structure. But when we tried to open that Investa, it just didn't know what to do, so it didn't plot those. So we could realize, oh, that's why it's invalid. It's using strings, characters instead of numbers there. Other times it's invalid because it will violate crystallography. For example, in this one, we know that it's possible to have multiple atoms sharing a site. A cation disorder, anti-site disorder is not atypical, but you can't have the overall occupancy be greater than 1. So if you say that lithium and silver both have the exact same site here, then you can't have them add up to more than 1. So that would be an invalid structure that was generated that way. And sometimes it's invalid based off of stoichiometry. If the formula was supposed to be 3 molybdenums and 12 aluminums, but it created 4 molybdenums, then you violated the stoichiometry, so that was invalid. Overall, though, it matches pretty darn well. Like here you see a bunch of histogram comparisons for the training data for energy above the whole and the generated data for energy above the whole. And basically it's matching. The lattice parameters are a match. The space groups are pretty much a match. The angles are pretty much a match. Like it's looking like it's doing a pretty good job of doing conditional generation based off of text guidance, which is pretty rad. And finally, I think the last slide I'll show you is this one, saying that not only does it look pretty good, if you look at sort of reduced order embedding of these space, not exactly the latent space, but if you do a PCA embedding or a TSNE embedding, the generated structures sort of have a very similar spread over these spaces that looks like we're getting pretty good coverage. Okay, I'm going to wrap up here. If there's I'm happy to take any questions. I'll point out that if you want to learn more about this, I'm an easy person to find. I've provided some of the links to where you can find us or our work right here. I'm happy to take any questions.